Hello everyone, welcome to Practically. We bring learning alive. So we are doing that class 10 one shot, and today we are having physics session. Let's wait for a few more minutes. Our friends may join. Yeah. So already chemistry, maths are started, and today's physics session, and the chapter is electricity. Okay, one of the important chapter, interesting chapter. And in term 1, if you see, we are having light chapter from where you are having numericals, whereas in term 2, from this chapter we'll be having numericals. So what sort of models will be given, or the concept, entire concept. So like a comprehensive teaching we are going to have today's session. Fine. Waiting for our friends. I think let them join. Few more minutes. Am I audible? Meanwhile, whoever are watching, is my voice clear to each and everyone? Yeah, you can reply. You can say something here. It is audible, yes. If not, no. Okay, fine. So see, so this is the one shot schedule that we are having for class 10. All right. Okay, thank you. See, this is the one shot schedule that we are having. It's already started, and today we are dealing with physics on 7th Feb, and 8th, 9th, 10 until 16th we are having one shots that consists of maths, physics, chemistry and biology, nothing but maths and science. Okay, and your tomorrow's one shot session is on mathematics, and then coding sessions are there even for class 10. The coding sessions on these dates: 5th Feb, 8th, 12th and 16th, 28th. So tomorrow you are having coding session on web services, and this is the timing 8 to 9:30. Okay, fine. Then let's enter into the session, our session, electricity. So coming to this chapter, as I said already, important, interesting. Apart from that, we know that regular usage of electrical energy, how important it is in our daily lives. All right, it's most convenient to use, even convenient to generate with the help of different methods. So what are the different generating methods and how this energy will be converted? Even in class 9 energy conversion you might have learned. Okay, so different sources of energy will be there. With the help of those we can develop this, we can generate electrical energy. So now we are talking about that electrical current. Okay, so straight away coming to the point, we are going to start this session with the concept called electric current. Fine. What is meant by electric current? How can we define it? So to define the electric current, we should know a fundamental quantity. It's not fundamental quantity, it's of course derived quantity. Current itself is the fundamental quantity. We should know the fundamental definition of it. So that is charge. I can say it is charge. What is meant by electric charge? Basically, electric charge is nothing but it's the fundamental property of a substance that can establish electrical forces among the objects. So that charge, we are having some different properties for charge, just like charge can be additive in nature. Okay, charge can be quantized. Quantization of charge is very, very important one. Quantization of charge is nothing but charge can be expressed in integral multiples of the number of electrons. Okay, that means we can write charge as Q is equals to plus or minus Nu. You are aware of this one, right? So here N means integer, E means charge of an electron. That means charge when you are about to add or remove, which actually we are expressing it now, it's in terms of electrons, right? you can add electrons or you can remove electrons. While expressing that adding or removing, you can express it in terms of integer numbers only. It's not decimal numbers. So that's what quantization of charge says here. Okay, so here n represents integer, E represents charge of an electron. Fine. SI unit of charge is coulomb. So this is the basic thing about electric charge. Charge is conserved, charge is additive in nature, charge is quantized. What is quantization of charge? This is the one. Okay. So now coming to electric current. How can we define electric current? It's very simple. The rate of flow of electric charge. The rate of flow of electric charge through a cross-sectional area of conductor is called electric current. I repeat, the rate of flow of electric charge through a cross-sectional area of electric current, through a cross-sectional area of a conductor is called electric current. We can express it as current I is equals to, so rate of flow of electric charge. So the charge varying with respect to time here. So current we can write it as current is equals to charge by time. Okay, charge we can represent with the letter Q and time T. So we can write I is equals to Q by T. This is the expression for the current in terms of charge and time. So we are having different expressions for current. In terms of voltage we can write, in terms of power we can write, in terms of energy we can write. Okay, so in this one at present, while defining electric current, how we are saying it as the rate of flow of electric charge or the flow of electric charge per unit time. Like that also you can write. So it depends on individuals. It's your choice. It both gives the same meaning. Okay. Rate of flow of electric charge or flow of electric charge per unit time through a cross-sectional area of conductor is called electric current. I is equals to Q by T. Then units here, very important. And I said already, SI current is one of the fundamental quantity. SI unit of electric current is ampere. It is represented by the letter A. And remember here, while writing the units, and if the unit, especially if the unit is the unit whichever is used for the physical quantity is name of the scientist, then all the letters, if you want to write the full form of that unit, then all the letters should be in smaller, lowercase. And if you want to represent only the symbol alone, then it should be in the capital letter. Okay, remember it, very important. So SI unit of electric current, here it is ampere, and here you are having next definition of ampere. How can we define 1 ampere? Okay, see that formula, we know electric current I is equals to Q by T, charge by time. If 1 coulomb of charge flows through a cross-sectional area of a conductor, in 1 second. So very important and very easy. If 1 coulomb of charge flows through a cross-sectional area of conductor in 1 second, then current flow through the conductor is said to be 1 ampere. From the formula, we can say here 1 ampere is equals to 1 coulomb of charge flows in a conductor in 1 second time interval. So then 1 ampere is equals to 1 coulomb by 1 second. Okay, hope I am clear with the electric current definition and as well what the definition of the ampere. So definition of the ampere, even they may ask like define the SI unit of electric current. They won't always ask you define 1 ampere. They ask you like define the SI unit of electric current. Simple, SI unit of electric current is nothing but ampere. So that you have to define 1 ampere only. Either you may be asked to define 1 ampere or define SI unit of electric current. Both are same. What is that? 1 ampere is equals to, if 1 coulomb charge flows through a cross sectional area of conductor in 1 second, then current flows through that is said to be 1 ampere. Okay, so remember it. Next one, yeah, here we are having a question based on that electric current. Let us see that question. A current of 0.5 ampere is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. Okay, so it's based on the concept of the strength of electric current. Okay, how we have expressed the electric current in terms of electric charge as well as time, right? Now this question, if you look at once, if you read it once, one more important point, while solving the numericals, especially of course this term 2 is going to be subjective. Okay, you are already aware of that. Even board has released some sample papers. In that also you might have gone through it, right? So while you are writing the subjective one, especially when it comes to numerical part, numerical portion, see, you just read the question. After read the question, you have to understand what is the given data and what you are supposed to calculate, and then write the solution by using the given data step by step, and then recall the suitable formula if any formula based content is there, or if any procedure is there, just follow the procedure step by step. You have to do it and obtain the final result. Suppose if any units are there for the finally obtaining quantities, you have to mention the units. If you are not forgetting the, if you are not mentioning the units, then definitely you will be losing the marks. Okay, so simple procedure. Read the given question, understand it. If you are unable to understand, read one more time and then write the given data, recall the suitable formula if existed. Then sometimes the interlinked formulas will be there. It may not be direct one. You may have to recall one more one, interlinking one. Okay, it depends on the question, but that won't be that much difficult from this chapter. Very interesting, important, easy also if you have understood the concept. And then substitute it. While simplifying also you have to be very careful. Okay, even so some children, they will do that recalling the formula, writing the data, everything properly, but while simplifying they may do the mistake and they may get the wrong result. Even if you get the correct answer, some students may use to forget the units, placing the units. So then that's all, it's gone. So each and every parameter is essential while answering numericals, especially in physics. Okay, so now let us see how can we solve this question here. A current of 0.5 ampere is drawn by a filament of an electric bulb for 10 minutes. Time is given and current is given. Find the amount of electric charge that flows through the circuit. Okay, we have to find electric charge. So see, what is the given data? So in the examination you have to write step by step. Here I am writing just by using the parameters directly. Electric current is given as I is equals to 0.5 ampere. Okay, and the time of flow T is equals to 10 minutes is given. Yeah, a very important thing, another thing, that is while solving the numericals in physics, you have to cross check whether all the units, the system of units, are they in same system or not. Doesn't matter if they are in SI system or CGS system. It's based on your convenience. But while substituting, you have to substitute the quantities by taking them in a common system. Okay, so anyhow, as we are talking about the SI unit system here, I'll check here whether all the quantities are in SI system or not. Current 0.5 ampere, it's in SI system. Yes, no issues. Time is given in minutes, but SI unit of time is not minute, it is second. So we have to convert this minutes into seconds first. That means 1 minute value in terms of seconds, 1 minute is equals to 60 seconds. So 10 multiplied by 60, that is 600 seconds. Okay, so time we know, current we know, and then what is the formula that existed with I, T and Q? So it's very simple. Current I is equals to charge by time. Our requirement is to find charge, keep charge there only, bring time to this side. So I multiplied by T here. Okay, that means Q is equals to current multiplied by time. Current value 0.5 time value 600. So see here, 6 5s are 30, one decimal is there, so 3 here, it is 300 coulomb, right? Okay, is it 300 or 30? It's 0.3, right? 0.3 into, just a minute. Yeah. Okay, 0.3. 6 5s are 30, one decimal is there. So 3 into 100, so 300, right? Okay, so that's how we can calculate electric current here by using this formula. Okay, now let's see the next one. Yeah, sorry. Yeah, potential difference. What is meant by potential difference? So many students used to confuse with this. Basically, what is meant by electric potential and potential difference? So see here, simply we can understand with the help of general water flow. Okay, so general comparison which you are already aware of, I hope so. See, if I say there is a level pipe, okay, if it is a level pipe, then flowing of water from this end to another end, it won't be happen, because there is no pressure difference. When water will flow in the pipe, when there is a pressure difference. So if you treat that flow of water as electric current here, I mean electric charge here, flow of electric charge, similar kind of terminology even we can talk over here. But instead of there, we are discussing about pressure difference that involves with many factors. So you can take a height difference, gravity, everything and all. But here that gravity or height, it won't play any kind of role in the while we are discussing electric current flow, electric charge flow. So then how this electric charge will flow through that conductor? Simple. There we have used that general pressure difference which causes that water pressure difference. Here we are going to express that same terminology as electric pressure difference. What is it? Electric pressure difference. So this electric pressure difference is the responsible for the flow of electric charge through the different points of the cross-sectional area of any conductor, whatever. So here that electric pressure difference only potential difference here. Okay, how can we define that potential difference? Potential difference of a conductor can be defined as, it is the amount of work done per unit charge to displace the charge between 2 points of a conductor, across 2 points of a conductor. So amount of work done per unit charge to displace the charge across 2 points of any 2 points of the conductor is called potential difference. Even we can write it as voltage also. So potential difference is equals to work done by charge. SI unit, if you see, SI unit of potential difference or voltage is volt. Okay, so here work done is expressed in terms of joule, charge is expressed in terms of coulomb, and potential difference we can even call it as voltage again. Okay, don't confuse here. So voltage, if you are asked to define voltage, then you can write the same definition, amount of work done per unit charge to displace it from one point to another point across the conductor. So then here when it comes to definition of volt, that's nothing but 1 volt. Define 1 volt. So definition of 1 volt you can define from its standard definition. If 1 joule of work is done to displace a charge of 1 coulomb, across 2 points of the given conductor, then the potential difference across the 2 points of the conductor is said to be 1 volt. Okay, suppose if I take this conductor having the potential difference, potentials at the points are A, VA and VB. Okay, so if 1 joule of work is done to displace this 1 coulomb of charge between these 2 points, then the potential difference across these 2 points is said to be 1 volt. Okay, so we can write 1 volt is equals to 1 joule by 1 coulomb. Just like how we have defined the unit definition of electric current. So here also you can be asked to define 1 volt or define SI unit of voltage. So same manner you can say, if 1 joule of work is done to displace the charge of 1 coulomb, then the potential difference between the 2 points across which the charge is displaced is said to be 1 volt. So 1 volt is equals to 1 joule by 1 coulomb. Okay, all right. Now let's move to the next slide. Yeah, there is a question on this one. Yeah, see here, how much work is done in moving a charge of 2 coulomb across 2 points having a potential difference 12 volt. Okay, so potential difference across the 2 points is given, which is 12 volt. We have to calculate work done. How much work is required to move this, to displace the 2 coulomb across the 2 points of the given conductor where the potential difference across the 2 points is 12 volt. So see here, we know that amount of work done per unit charge to displace from one point to another point along the conductor is called voltage or potential difference, whatever. So then, so according to given data, voltage is given or potential difference is given across the 2 points, that is 12 volt, and charge is given, the charge is 2 coulomb. So we have to calculate work. So then we know that, recall the formula, potential difference or voltage is equals to work done per unit charge, right? So then V value how much, children? It's 12 volt. Work how much we have to calculate. Charge is given, which is 2. Then W is equals to, if you multiply, cross multiply, 12 into 2 you will get, so 12 2s are 24. 24 joules of work is required to displace the 2 coulomb of charge along the 2 points of the conductor. Okay. Yeah, Aman. Hi, Aman. Fine. So see here, the amount of work that is required to displace this charge is 24 joule. See, just we have recalled the concept and I applied the formula. Nothing else I did here, right? Let's move to the next question. Okay, fine. Some symbols of electric components. So in electrical terminology, we are going to use some special electrical symbols to represent like a bulb or voltage source or wires or switch. So there are some symbols. Now let us see the symbols and all. Okay. Okay, I am starting with a cell, general one. Cell we can represent by drawing 2 terminals like this. So while drawing these 2 terminals, be careful. One should be longer terminal, other should be shorter terminal. The longer terminal basically will represent it as positive terminal, and the shorter one will represent it as negative terminal. So be careful, they should not be equal in lengths. If you are marking equal in lengths, the terminal lengths are equal, then that will be called as capacitor. So it will be different one. Okay, so be careful. So this is the symbol of a cell. Next, battery. Battery is the combination of the cells, okay, which are connected like this. Okay, sorry. So when you are starting it with longer terminal, longer, shorter, and then longer, shorter. That's all. So here positive, and that should end with negative. So be careful. Positive, negative, positive, negative, positive, negative. This is the symbol of a battery. Next, ammeter. Ammeter is a device that is used to measure the electric current. So this is the symbol of an ammeter. Okay, so polarity is important. Mention that plus and minus polarity. Next, and if you look at, if you observe that ammeter and all in the laboratory, there will be those two knobs will be colored as red and black. Red is for a phase wire and black is for neutral wire. So that's what polarity and all I am representing here. Okay. Yeah. Next, voltmeter. Ammeter is used to measure the electric current flowing through the conductor. Voltmeter, this is the symbol of voltmeter that is used to measure the potential difference across the 2 points of the conductor. Next, switch. So here switch again, if it is a tab key, if you are representing, okay, so this is the representation of your tab key off. Okay, switch on. Okay, this is switch off and this is switch on. Switch on means you have to close this. This is tab key on. Okay, next one. So in that switch again, plug key also we are having. Plug key on. So this is how you have to represent plug key on by putting the dot over here. Plug key off. So if you are removing the dot, that means plug key is off condition. Okay, next, electric bulb. This is how we have to represent the electric bulb. Next, resistor. So this is the symbol of a resistor. Okay, and in this variable resistor also there. So variable resistor we can mark like this by drawing the arrow line. You can make it, I mean, if arrow line is drawn across it, then you can call it as the resistance is variable resistor. In this variable resistor itself, rheostat is there. So the representation of rheostat is like this. So that is also a kind of variable resistor. Okay. Just a minute. Okay, so this is the representation of rheostat. Next, electrical wires. Wires can be represented by drawing some solid lines like that, thick lines. Okay. Next here, wires with joint, without joint. Wires without joint, here I am drawing. See, if this is one wire, another wire without joint, you have to draw like this. So if the two wires are represented like this, it means there is no contact between these two wires. So instead, if you are representing directly like this, it means wires with joint. Okay, so these are the general symbols, electrical symbols that we are using while drawing these electric circuits. Okay, fine. Cell, battery, ammeter, voltmeter, switch off, switch on. So this switch is tab key. This is plug key on, plug key off, bulb symbol, resistor, in that variable resistor, rheostat, and electric wires without joint. This is without joint, this is with joint. Okay. Yeah, let's move on to the next one. Ohm's law. Okay, fine. So we have discussed those components, what are the electrical symbols and all, right? So I will give a simple definition for electric circuit. Electric circuit is nothing but it's a closed path. Electric circuit is nothing but a closed path that consists of electric appliances, voltage source, switch, and electric wires, so that a path for the flow of current will be provided. So electric circuit is a closed path that provides a path for the flow of current. So which consists of voltage source, electrical appliances and electric wires along with the switch. Okay. So any closed path you may take that consists of all these voltage source and devices, wire, switch and all. Then in that closed path electric current will flow. Current never flow in the open circuit. It will flow only in the closed circuit. So that we are calling it as electric circuit. Okay. So when there is an electric circuit, such electric circuit you may take. I am taking here an electric appliance that consists of some resistor generally, whatever. Okay, it's connected to a voltage source with the help of a switch like this. Okay, now switch closed, let it is. Resistance of the resistor is R. Then the voltage source is having some voltage, let it be V volt, or else EMF is V volt. So as it is a closed path, just now I said in the closed path electric current will flow. Let the amount of current that is flowing through that, it is I. So here when the current flows through here, then voltage drop is existed across this resistor. Okay, the voltage drop that exists over here, let it be V. Okay, now coming to the statement of Ohm's law, very important. When the physical conditions are unchanged, physical conditions are like temperature. Okay, so you can say at constant temperature. Very simply you can say that at constant temperature, current flows through a conductor is directly proportional to potential difference applied across it. Okay, so see, the same conductor I am taking, whatever the electric current, electric conductor, whatever the resistance that is, if the same conductor I am taking, it is having a resistance R. Okay, now the voltage applied across it is V for a flow of current I. So according to Ohm's law, at constant temperature, according to Ohm's law, at constant temperature, the amount of current flows through the conductor is directly proportional to potential difference applied across it. So we can write that statement as V proportional to I. Okay, by removing this proportionality, we can place a constant. Let the constant is R here. So we can write V is equals to IR. Okay, so this we can remember with the help of a simple magic triangle like this. V I R. Whichever you want to find, you can just close that letter. Suppose if I want to find voltage, so V is equals to I multiplied by R. If you want to find current I, then I is equals to V by R. If you want to find resistance, R is equals to V by I. Just like that you can remember. So here R means resistance. The proportionality constant what we used is R. R means resistance. Very important. So this is Ohm's law, children. Very important and very easy too. At constant temperature, electric current flows through a cross-sectional area of a conductor is directly proportional to the potential difference applied across that. Across the conductor. That is V proportional to I. V is equals to R multiplied by I. V is equals to IR. Whereas R is what? Proportionality constant that represents resistance. Okay. Yeah. So now there is a question on the Ohm's law. Let us see. Potential difference between the terminals of an electric heater is 60 volt. Okay. When it draws a current of 4 ampere from the source, what current will the heater draw if the potential difference is increased to 120 volt? So see here, there is an electric heater. That electric heater, when it is operated between 60 volt, when there is a potential difference of 60 volt, current that is drawn by it is 4 ampere. The same electric heater, if it is operated between this 120 volt potential difference, then what will be the amount of electric current that is drawn by the heater? So here one thing that you should understand is, when the before changing the voltage and after changing the voltage, the device used is common, which means only the same electric heater is used when it is operated under 60 volt and when it is operated under 120 volt. So voltage is changed but device is not changed. That means the resistance what it is having will remain same when it is operated under 60 volt or when it is operated under 120 volt. That's the important point that should be noted here. Okay, so here what I am doing, potential difference between the terminals of an electric heater is 60 volt. When it draws a current 4 ampere, they said. So when 60 volt case if I am taking, okay, when 60 volt potential difference is applied, then so I is equals to 4 ampere, V is clearly 60 volt. We know that according to Ohm's law, V is equals to IR, just now we discussed, and then R I am calculating by using this data. V value is 60 and then I value is 4, 60 by 4, 415s are. So resistance of the heater is 15 ohm. Now when the same heater is used but voltage is 120 volt now, since they said when the heater draws, what is the current that heater will draw when the potential difference is increased to 120 volt? Potential difference is 120 volt and then current we have to find. I is equals to applying Ohm's law, V by R, V value 120 but R value, as I said, the heater is same here, so same resistance will be there, 120 by 15, 15 8. So I is equals to 8 ampere. Okay, so this is how we can use the Ohm's law to solve the numericals. All right. Yeah, let's move on to the next slide. Resistance. So we discussed in Ohm's law, while we are discussing Ohm's law, we have got one proportionality constant. That constant we named it as resistance. So then what is meant by resistance? See, resistance is nothing but it is the property of a substance that can oppose the flow of electric charge through it. Okay. The property of a substance to oppose flow of electric charge. To oppose flow of electric charge. Okay, so here all the materials they won't be having same resistance. Based on the amount of resistance that is presented or based on the amount of opposition that is offered by the material, these materials are divided or classified into three types mainly. They are conductors, insulators and semiconductors. Conductors are the materials which allow the electric flow of charges through them. That means even they too will be having resistance. It doesn't mean that conductors are not having resistance. Ideal conductor's resistance is 0, but ideal conductor is not existed. Okay, we are having that superconductors and all, and that too some under some special cases we will obtain it. So basically in general if we talk, so ideal conductors, if you take, resistance is 0, but general conductors, whatever the best conductors you may take, like copper or aluminum or all the metals which are existed, so they will be having less resistance. It doesn't mean that they are not having resistance. They will allow the electric charge, still they will be having resistance, but that is very low opposition. So low opposition is offered to the flow of electric charge when it compared to the insulators, that other one. So okay, whatever. Conductors are the substances that will allow the flow of electric charge through them. And if you see the metals, copper, aluminum, iron, those and all will be come under conductors only. Insulators, very important one. The materials which do not allow the flow of electric charge through them, they are called insulator. So just like rubber, plastic, okay, jute stick, these and all are the examples for the insulators. So even that is the reason why these electrical works, when they are doing, so they used to wear the rubber gloves, rubber shoes. So because rubber is an insulator, it will prevent from the electrocution. It's like getting electric shock, that will prevent from it. So okay, and another third one is semiconductors. Semiconductors will allow the partial flow of electric charge, okay, like silicon, germanium, etc. Conductors, they will allow flow of electric charge. Insulators, they do not allow the flow of electric charge through them. Semiconductors will allow partially. Conductors example, all the metals. Insulators, rubber, plastic, wood, dry wood, jute stick, etc. Semiconductors, this silicon, germanium, etc. Those things you may consider under the examples of semiconductors. Okay, fine. So whatever generally resistance means, it is the property of a substance that can oppose the flow of electric charge through them. Okay, so very important one. Now SI unit of resistance is ohm. So even resistance is also one of the derived quantity. The SI unit of resistance is ohm. Symbolically we can write it as like this. It's called omega, Greek letter. Okay. How can we define ohm? So from Ohm's law, we know that V is equals to IR. Alright. So then resistance R is equals to, we can write it as V by I. If 1 ampere current flows through a conductor, when a potential difference of 1 volt is applied, then resistance of the conductor is said to be 1 ohm. So see here, resistance of the conductor is said to be 1 ohm. If 1 volt potential difference is, if 1 ampere current flows through the conductor, for a potential difference applied 1 volt across the 2 points of the conductor. So alright, 1 ohm is equals to 1 volt by 1 ampere we can write. So this is about the resistance, simple statements. Opposition offered by the substance to the flow of electric charge is called resistance. Generally these alloys, metals will be having low resistance. Okay, their order is that we can express in terms of resistivity also. Resistivity is defined from with the help of resistance. So there I will tell you what are the ranges of conductors, I mean resistivity of conductors, resistivity of insulators and all. Okay. Sorry, the next one. Yeah, ohmic conductors. So we have seen Ohm's law. What is the Ohm's law? At constant temperature, current flowing through the conductor is directly proportional to the potential difference applied across it. And there we have written V is equals to IR. Okay, leave it. So now all the conductors which we are having, they won't obey the Ohm's law. Only few conductors will obey Ohm's law, few do not obey Ohm's law. So the conductors which obey Ohm's law are called ohmic conductors. Simple, children. Okay, conductors that obeys Ohm's law are called ohmic conductors. So those ohmic conductors, how can we get to know that conductor is a ohmic conductor and that conductor is a non-ohmic conductor? Simple. In laboratory, if we conduct that Ohm's law experiment, after conducting that, if you plot the graph between V and I, voltage and I values, then if we get the graph straight line, then we can say that conductor is obeying Ohm's law and it is called as ohmic conductor. Ohmic conductors, or we can call it as linear conductors also. Why linear conductors? Since the graph which is plotted between V and I is linear. Okay, so that's why we'll call them as linear conductors or ohmic conductors. On the other hand, some conductors which are there, they won't obey the Ohm's law. So the conductors are the materials which do not obey Ohm's law are called non-ohmic conductors. So if you plot the graph between V and I for that such kind of conductors, then the graph will be non-linear. It won't be linear. As the graph which is plotted between V and I parameters is non-linear, so we can also call them as non-linear conductors. Okay. Conductors that obey Ohm's law are called linear conductors. Conductors which do not obey Ohm's law are called non-linear conductors. Ohmic conductors are also called linear conductors since the graph plotted between V and I is linear. And non-ohmic conductors are also called non-linear conductors since the graph that is plotted between V and I will be non-linear. Okay. So if you see that ohmic conductor example, we can take any copper wire or copper conductor or aluminum conductor, those metallic conductors we can take. Non-ohmic conductors, if you see this thermistor, okay, PN junction diodes and all, if you see, those will be having non-linear characteristics. Okay, fine. So this is about ohmic conductors and non-ohmic conductors, very important and easy to. Yeah, another important one, factors on which the resistance of a conductor depends. So what is the resistance? Based on that resistance property, how the materials are segregated, we have seen. Now the next one is on what and all factors that resistance of the particular conductor is going to be depend on. Okay, so see here, resistance of this conductor will depend on length of the conductor, very very important. Length of the conductor. That to how it is related, resistance of the conductor depends on the length by having a directly proportional relation. Resistance is directly proportional to the length of the conductor. It depends on area of the conductor. To the area, resistance is inversely proportional. Okay, so let this is 1 and let this is 2. Apart from these two, it depends on the nature of material. So different materials will be having different resistance. It's not that all the materials will be having the same. So the material which is made of copper will be having one value of resistance. The material which is made of aluminum will be having another value of resistance. So based on the nature of the material also, the resistance will be varying. And then physical factors such as temperature, very important one. Okay, temperature changes, the resistance also affected. So these are the main 4 factors that on which the resistance of the material will depends on. Length of the conductor, area of the conductor, and nature of the material, as well as temperature. So here to the length, how it will vary? By having a directly proportional relation, and to the area, that will be having inversely proportional relation. That means if you keep area constant and if you are having length alone, if you are increasing length, resistance also increases. Okay, and by keeping length constant, if you see the area, if you increase the area, resistance decreases, and if you decrease the area, resistance increases. Inversely relation. Okay, so from these 1 and 2 parameters, we can write here R proportional to L by A. Okay, so here by removing proportionality, we can mention this is equals to by having a proportionality constant rho. This is rho L by A, very very important. So this proportionality constant, what is this? Rho, Greek letter rho, that is, it is called as resistivity. Resistivity, we can also call it as specific resistance. Okay. So these are the factors on which the resistance of the material will depend on. Very, very important. Resistance of the conductor depends on length of the conductor, area of the conductor, nature of the material, temperature. Okay. To the length directly proportional relation, to the area it is inversely varying. Okay. Let's move on to the next slide. Yeah, so in that we are having specific resistance. What is that? Rho is equals to, sorry, so there resistance R is equals to rho L by A we got. Alright, so where rho is equals to RA by L I will write. Okay, how can we define the resistivity or specific resistance? Just now I said specific resistance is also called as resistivity. Rho is equals to RA by L. Here, if area of cross section of the conductor is 1 meter square and length of the conductor is 1 meter, then resistivity will become rho is equals to R into 1 by 1 that is equals to R. So we can say here resistivity of the conductor can be defined as it is the resistance of the conductor having 1 meter in length and 1 meter square area of cross section. That means in unit volume, how much resistance will be there? That will be the resistivity of that material. So see here, you may take a resistor, you may take a conductor, any material having 1 meter in length, 1 meter square area of cross section. In that, how much resistance will be there? That will be the resistivity of that material. So this resistivity throughout this conductor, throughout that material, same amount of resistivity will be there. Whether the length increases or area increases or length decreases or area decreases, doesn't matter. So resistivity is independent on the dimensions of the material. Resistivity does not depend on the length. It does not depend on the area. Okay, in unit volume, or else you can say in the material which is having 1 meter in length, 1 meter square in area of cross section, how much resistance is there? That will be the resistivity of that material. Okay, so that's why I said resistivity is defined as the resistance of the conductor having 1 meter in length and 1 meter square area of cross section. Any material generally you may take. So numerically you can express like this, and from this formula rho is equals to RA by L. Okay, SI unit of resistance is ohm, SI unit of area is meter square, SI unit of length is meter. This get cancelled. Then SI unit of resistivity will become, children, ohm meter. So ohm meter is the SI unit of resistivity. Don't confuse with the terminology. Specific resistance is different and resistance is different. Specific resistance is also called resistivity. Again I am saying resistivity is independent on length and area. Then on which factors it will depends? It depends on temperature and it depends on nature of the material. Okay. It is independent on the dimensions of the material such as length and area. All right. Okay. So that's about specific resistance. And there is a question based on that resistance concept. Let us see. A wire of given material having length L, this is length L, and area of cross section A has a resistance of 4 ohm. All right. What would be the resistance of another wire of the same material having length L by 2 and area of cross section 2A? So see, very important model. Here both length and area both are changed. Then how can we calculate the new resistance? Suppose if length alone is changed by keeping area constant, in what ratio length is changed, in the same ratio resistance also will be changed. Increases or decreases doesn't matter. Okay, for both it is same. Whether increases or decreases, both same. In what ratio length is changing? By keeping area constant. In the same ratio resistance also changes. Similarly, by keeping length constant, in what ratio area is affected, area is changed, in the same ratio resistance also will be changing. Inversely proportional, but here that means if area increases, resistance decreases by the same amount. If area decreases, resistance increases by the same amount. In this particular case, if you see both length and area both are changing, then how can we calculate? See, what would be the resistance of another wire of the same material having the length? Okay, this is another wire. Okay, no issues. We know that R is equals to rho L by A. This is for the first wire. So for that wire, LA is given and area A, sorry, length L is given, area A is given, rho is the resistivity of the material, then this value is 4 ohm. Another wire which is made of the same material is taken, the same material they said, so then new resistance I am taking it as R dash, that is equals to, as they said same material, so rho remains same, since see same material they said. L, what is the new length now? I mean another material, another wire which is made of same material, that length is L by 2 and that area is 2A, 2 times of A. So here rho L by A, this 2 comes to denominator, 2 2s are 4. So it means R dash is equals to 1 by 4 times of rho L by A. 1 by 4 times of, but rho L by A means what? 4 ohm. So 1 by 4 times of 4, 4 get cancelled, this is 1 ohm. Alright, so the new resistance value is 1 ohm. Clear? So this is how you can solve such type of questions. Okay, let's see the next one. Resistance of a system of resistors. Alright, so generally these resistors can be connected in various combinations. Okay, mainly there are 2 combinations in which these resistor systems can be connected. So they are, one is series combination and secondly parallel combination. Okay, series combination of resistors. Generally series combination is nothing but, we can say it as end to end connection. That means if I take 2 resistors like this, okay, if I join the end of one end of this resistor and another end of this resistor like this, this is called end to end. End to end connection is series connection. Parallel connection, if suppose same resistors I will take, similar ends are joined simultaneously. So these are the 2 ends, right? Similarly, these are the 2 ends. If I join like this, then that will be parallel connection. So here when the group of resistors are connected in series, what will be the effective resistance? When the group of resistors are connected in parallel, what will be the effective resistance? How can we calculate when they are given 2 resistors, 3 resistors? Let us see now. Okay. So now resistors in series, 2 combination. Okay, fine. Let us consider 2 resistors having resistance R1 and R2. Okay. they are connected in series as shown in the figure. Now let these two are connected to a voltage source having voltage V volt I am taking. Alright, as it is a closed circuit, I amount of current will flow through the circuit. Okay, so here comes the important point. In series connection, remember, in series connection, voltage will be divided, whereas current through the each resistor will remain same. Current through the each resistor will remain same, whereas voltage will be divided. That means in this, if I say I is the amount of current that is flowing through this resistor, then through this resistor I will flow. Even here also the same amount of current will flow, that flows and will return to the circuit, voltage source like this. Okay, so see here, current direction in the closed path, always we are taking conventional direction. Conventional current direction is always from positive to negative. Very, very important. Okay, but electron current direction is from negative to positive, which is opposite to this. But generally we are preferring conventional current direction only. That should be always taken from positive to negative. Very, very important, remember. Okay, fine. Coming to the point, when the resistors are connected in series, then across the each resistor there will be a certain potential drop based on the value of the resistance, but electric current that flows through each and every resistor remains same. Okay, so then if I say the voltage drop across this resistor is V1 and voltage drop across this resistor is V2, by using Ohm's law, okay, we can write here the total voltage drops that are existed will be equals to the source voltage. So V is equals to V1 plus V2. So by using Ohm's law, V can be written as total amount of current multiplied by the total amount of the resistance that offered by this circuit. So that V is equals to IR I am taking, and V1 is nothing but, again I am applying the same Ohm's law. V1 is the voltage drop across this resistor R1. Across that resistor current flows is I. Resistance of that resistor is R1. So V1 is equals to IR1. Similarly, V2 is the voltage drop across this resistor R2. So V2 is equals to IR2. Okay. Then substitute there. IR is equals to IR1 plus IR2. As current remains common, take it common. So I is equals to IR is equals to I into R1 plus R2. So I cancel on both sides. R is equals to R1 plus R2. So this R you can write it as R effective is equals to R1 plus R2. So this you can name it as effective resistance or net resistance or total resistance, okay, or overall resistance, whatever the name that you may give, doesn't matter. So in series combination, the final result, if you see here once, effective resistance is the sum of the individual resistance that are given in the circuit. Okay, so whatever the resistors that are given, those resistance addition, if you add, that will be the overall resistance of that series circuit. So in series combination, when there are resistors which are having some resistance, if you want to calculate the overall resistance of that combination, then you have to add simply, that's enough. That will give the overall resistance of the circuit. Okay, so in series combination, the net resistance is equals to sum of the individual resistance. All right, so this is for two combinations, two resistors in series. One point that you must remember is, in series combination, current through each and every resistor remains the same, but potential difference will be the voltage drop will be existed based on the resistance of that resistor. Very important. So here it may not be always the resistor means it may not be that same resistor that we are going to have, that small things which we are having in the laboratory. It may be any electrical device, any device, even our human body also will be having some resistance. Okay, so it doesn't matter that there may be electrical devices, electrical appliances, electrical components they mention over here, doesn't matter. Okay, so this is how we can obtain the series effective resistance for a combination of two resistors when they are connected in series connection. Okay, now let's see the same resistors in series for the three resistors. Consider three resistors having resistance R1, R2 and R3 that are connected in series across a voltage source with the help of these connecting wires like this. Okay, so current flowing through this circuit, let it be I. As I said, in series combination current remains same through each and every resistor, whereas potential difference will be varying. So let V1 is the voltage drop across the resistance R1, V2 is the voltage drop across the resistor R2, V3 is the voltage drop across resistor R3. And by using Ohm's law, we can say here V is equals to IR, whereas R is the total resistance of the circuit. V1 is equals to IR1, since I remains same through each and every resistor here, and V2 is equals to IR2, V3 is equals to IR3 similarly. So here V is equals to, we can write the sum of these voltage drops will be equals to the source voltage. Okay, V is equals to, we can say V1 plus V2 plus V3. Okay, V means what? IR. IR is equals to V1 means IR1 plus IR2, V3 means plus IR3. So here I common again, IR is equals to, I take common R1 plus R2 plus R3. I get cancelled. R is equals to R1 plus R2 plus R3. So see here, in the previous one, when two resistors are given, total resistance of the series combination is sum of those two resistors, resistance of the resistors. When three are given, R1 plus R2 plus R3. When such kind of resistors n number is given, like R3, R4, Rn, then you just have to add it. R is equals to R1 plus R2 plus R3 plus so on plus Rn. So the main important conclusion that you have understood, you have to understand from this concept is, in series combination, the overall resistance that is offered by the circuit is high, is greater than the greatest resistance. Overall resistance of the series combination is greater than the greatest resistance in that circuit. Suppose if I say this value, R1 value is 1 ohm, R2 value 2 ohm, R3 value 3 ohm. What is the greatest value here? 3 ohm. Okay, fine. Now if they are connected in series, let them, then RAB is equals to, according to the series concept, 1 plus 2 plus 3, that means 3 plus 3 6 ohm. So the value of this combination is offering high resistance. That too, that value will be greater than the greatest resistance among these values. Among these values, this is the 3 ohm which is greater. So in series combination, the result will be greater than that greatest resistance. That is the important point. So series combination, total resistance of the series combination is great, will be offering a high resistance and that resistance is greater than the highest resistance in the combination, just like this. This is the example. Next, another important drawback of this series combination is, suppose, as I said just now, this may not be always resistor. You may take any electrical appliances, so that bulb or fan, whatever you are having at your home, you may take. If those electrical appliances or those electrical devices are connected in series, then suppose if any one electrical appliance will fail to operate, suppose there are 3 bulbs over here. If bulb 1 fails to operate, then bulb 2 and bulb 3 also will stop function simultaneously. They won't function. That's the major drawback. Okay. One drawback is series combination will offer high resistance. Another drawback is if one electrical appliance will fail to operate in the series combination, then others also will stop functioning. Then the third one is the voltage is not same. Voltage applied is not same across each and every resistor. It will be varying based on the resistance also. That means voltage division is occurred over here. So these are the major drawbacks of series combination, and by using these, I mean, to overcome this series combination, we are having another one, that is parallel combination. Whatever the drawbacks that I said here, that all those drawbacks can be overcome by the parallel combination. Alright. So this is how the series combination of resistance will be. Now let's see that parallel combination. Okay. And before entering into the parallel combination, 2 things that I will recall. One is, while solving this series combination, current flow through each and every resistor remains the same, and then voltage drop will be existed based on the value of resistance. Okay, another one, drawbacks. If you see, in series combination of the resistors, the effective resistance will be greater than the greatest resistor, greater than the greatest resistance in the combination. Next, if any one electrical appliance fails to operate, others will also stop functioning. Next, voltage is not, I mean, voltage division will be occurring in the series combination. Now let us see the parallel combination. Okay. So resistors in parallel, 2 resistors I am taking that are connected in parallel. I said in series combination, I mean, that is the end-to-end connection. How to connect in parallel? Don't judge the type of connection based on its geometrical structure. I mean, suppose if the resistors, like you may take, so now this, suppose 2 resistors are given which are connected like this. Now we can't say they are in parallel. We should not say they are in parallel. They are in series only. See, this is end-to-end connection. One end of this resistor is connected to another end of the another resistor, and we are calculating resistance between A and B. So this is nothing but this only, A, B, R1, R2. So this is series combination only. So don't judge the type of connection based on its geometrical shape. That's very important. So now here, parallel combination is a similar end connection. We are talking about 2 combinations. Okay, I mean 2 resistors. Let us take 2 resistors having resistance R1 and R2 as shown in the figure. They are connected parallelly across a voltage source as shown in the figure. Okay, now let current flow through this combination is I. Now when it comes to resistors here, these are connected in parallel. So this is called node, NODE, node or junction you may say. So at this node point or this junction point, this current will be divided as I1 and I2 as shown in the figure. Again this I1, I2 will come like this, and here they will be merged as I again. So we can say I is equals to I1 plus I2, very important. Alright, so because I1 and I2 together will be giving I here. There we can apply junction rule, of course. So in parallel combination, the very important point here it is, current through each and every resistor, it will be, I mean, current divides through the resistors, whereas the voltage applied, I mean voltage across the resistors is same as the source voltage. Whatever the voltage that is there for the source, same will be occurred, same will be existed, or same will be appeared across the resistors that are there in the parallel combination. So across resistance R1 and R2, source voltage only will be there. Voltage across here it is V, voltage across here also it is V, source voltage. That is the important point. Okay, all right. So according to Ohm's law, we know that V is equals to IR, then I is equals to V by R. Similarly, current I1 is equals to, I1 we took it as current flow through the resistor R1. So I1 is equals to, their voltage is V, their resistance is R1. So why voltage V here? Just now I said in parallel combination, whatever the source voltage is there, same source voltage will be appeared across the resistors that are connected in the parallel. See, suppose if you take one more resistor here, then also same will be there. One more you may take, same will be there. But another resistor here if you take in series, then across this and this voltage remains same, but it won't be source voltage. Because if any another resistor in series, if it is there, some voltage should be dropped, that voltage will be dropped across that series resistor. Then remaining will be appeared across here and here. So that is a very important point. So in this combination, there is no any other series resistor here. Only these two resistors, that too they are in parallel. So the same source voltage whatever is there, that will be applicable here and here. Then I1 is equals to V by R1, I2 is equals to V by R2. So I is equals to I1 plus I2. Then from this we can write here V by R is equals to V by R1 plus V by R2. As V is common, it will be 1 by R. V common I am taking 1 by R1 plus 1 by R2. So V get cancelled. We will get 1 by R is equals to 1 by R1 plus 1 by R2. So see here, in parallel combination, the reciprocal of the overall resistance. Here R is this 1 by R, I am taking it as R effective. That R effective is equals to 1 by R1 plus 1 by R2. So the reciprocal of the overall resistance is equals to sum of the reciprocal of the individual resistance. I repeat, reciprocal of the overall resistance of the parallel circuit or parallel network is equals to sum of the reciprocals of the individual resistance. Okay. For this one, after finding this value, you have to take the reciprocal. Then this 1 by R1 plus 1 by R2 is the 1 by R effective. But R value, if you want in parallel circuit, you should take the reciprocal of that. Or else, if there are two resistors, you can apply directly. If you simplify this, R effective is equals to, we will get R1 R2 by R1 plus R2. If only two resistors, if you want to simplify, directly you can apply this formula R1 R2 by R1 plus R2. You no need to take the reciprocal further. If you are using this formula, then to find R effective, you should take reciprocal of the final value. And if you are using this formula when the two resistors are given, then you no need to apply you no need to take the reciprocal of the final value. That means, suppose if it is 2 ohm, if it is 3 ohm, okay, if I am using this formula, R effective is equals to 2 into 3 by 2 plus 3, 6 by 5 ohm. Enough. You no need to take the reciprocal. That itself is the answer. If you are using this formula, 1 by R effective is equals to 1 by 2 plus 1 by 3. LCM 6 here, 2 3 times, 3 2 times, 5 by 6. But this 5 by 6 is 1 by R effective value. We want R effective. Then R effective is equals to 6 by 5 ohm. So that's what I said. If you are applying this directly to solve this combination of resistors that are in parallel, two resistors in parallel, R1 R2 by R1 plus R2. And this is the standard formula. Okay. So that's what, be careful while using this one, because many students, they will be in that hurry, they won't take that reciprocal and they leave like that. So be cautious, be careful. Okay, so this is how you have to solve when the two resistors are connected in parallel combination, parallel connection. Now let us see when the resistors in parallel, when the three resistors are in parallel, how can we solve? Consider three resistors having resistance R1, R2, R3 connected across a voltage source like this. Let I is the current flowing through this combination. Okay, and here, as I said, this is the node point. Let the current through R1 here, let it is I1, through R2 let it is I2, through R3 let it is I3. As I said, there is no any other additional series combination to this existed parallel. So whatever the resistance that is there here in the source voltage, whatever the voltage is there for the source voltage, the same source voltage will be applied across all the three resistors. So then the voltage here it is V, here also V, here also V. Since V I have taken as the source voltage. Alright. And whatever the current that will be here I1, here I3, I2, I1, they will be added here as I again. That means I is equals to I1 plus I2 plus I3. Okay, according to Ohm's law, V is equals to IR, then I is equals to V by R. Similarly, here in this case, I1 is equals to, we can write, so I1 is equals to, we can write here voltage, here voltage by their resistance. Okay, so V by R1, I2 is equals to V by R2, I3 is equals to V by R3. Alright, so then I is equals to, we know that I1 plus I2 plus I3. Then V by R is equals to V by R1 plus V by R2 plus V by R3. Alright, so V by R, take V common, then we'll get here 1 by R1 plus 1 by R2 plus 1 by R3. V get cancelled, then 1 by R is equals to 1 by R1 plus 1 by R2 plus 1 by R3. So then effective resistance when three resistors are connected in parallel can be written as like this. So same children, the effective resistance in the parallel, reciprocal of the effective resistance is equals to sum of the reciprocal of the individual resistance. Okay, and here the points that should be noted. Point number 1, in parallel combination of the resistors, the resistance offered is overall resistance is lesser than the least resistance. In series combination, overall resistance is greater than the highest resistance, highest value. In parallel combination, the overall resistance is lesser than the lowest value. That means I'll show you here. In the previous case, if you see here, I gave an example. When you have taken this as 2 ohm, this as 3 ohm, the least value is 2. Least value is 2. So the combination of these two resistors value is 6 by 5. 6 by 5 means some 1 point change. Okay, some 1 point something. So the value of the resistance in parallel combination is less than the lowest value here. In series combination, overall resistance is more than the greater than the greatest value. So the conclusion is here, in parallel combination will offer the least resistance, series combination will offer the highest resistance. There it is highest than the greater than the highest resistance, highest value. In parallel combination it is lower than the least value. Next, in parallel combination, another advantage. Suppose if I say these are the 3 bulbs, if I am operating here, if one bulb failed to operate, then others will function as usual. Nothing happens to the other devices, rest all will function as usual. But in series it is not like that. If one appliance or one device fails to operate, fails to function, then other will also stop functioning. In resistance in the parallel combination, one will not function properly, then the remaining will work as usual. So that's why all the electrical appliances, these domestic connections and all preferred in parallel combination only. It's not series combination. So each and every electrical device will be operated individually. Whichever we want, we will operate it. Whichever we don't want, we won't. Okay, so that's how. And another important advantage of parallel combination is whatever the voltage that is there in the source voltage, same voltage will be appeared across each and every appliance that are connected in the parallel combination. That's the important point. Okay, so this is about the resistors in parallel combination when 3 resistors are given. Now based on these combinations, okay, let us solve one question on it. Okay, in the figure you are given the diagram over there. Okay, in figure resistors, 3 resistors are given, R1, R2 and R3, R4, sorry, 5 resistors are given, R1, R2, R3, R4, R5 with some values 10 ohm, 40 ohm, 30 ohm, 20 ohm, 60 ohm respectively, and a 12 volt battery is connected to the arrangement as shown in the figure. Calculate the total resistance in the circuit, total current flowing in the circuit. So totally you are asking. Fine. Total voltage is given, that is a 12 volt battery they said. So this is 12 volt. So we have to find the overall resistance value first of all. The combination of these two resistors, I am taking it as R dash. R1, R2, they are in parallel. I took them it as R dash, overall resistance of those two. R3, R4, R5, these 3 are in parallel again. I am taking this as R double dash. So first I am calculating R dash. R dash is equals to, only 2 resistors are there, I will apply direct formula, that is R1 R2 by R1 plus R2. In fact those two values also R1 R2. R1 value 10, R2 value 40. So 10 multiplied by 40 divided by 10 plus 40, that is 400 by 50, that is 58 times, right? So it is 8 ohm. R dash value 8 ohm, children. Okay, right. Next R double dash. So there are 3 are there. When 3 are there, I am applying this normal one. 1 by R double dash is equals to 1 by R3 plus 1 by R4 plus 1 by R5. R3 value 30 ohm, R4 value 20 ohm, R5 value 60 ohm. Okay, so here it's very clear. 1 by R double dash is equals to, LCM is 30, 20, 60 means 60, 32 times, 23 times, 61 times. So we'll be having 6 by 60, that is 1 by 10. 1 by 10 is 1 by R double dash value, but R double dash value is what? 10 by 1, that means 10. So 10 ohm. But if you look at here once, this R dash and this R double dash, now if you redraw that diagram, it will become, this is source voltage, this is R dash and this is R double dash. How they will be? They are in series now. This R dash and this R double dash will be in series. So overall resistance between those two, between these 2 points, if I say, in fact that is closed circuit, overall resistance is equals to R dash as they are connected in series. So you can add now R dash plus R double dash, that is 8 plus 10. 8 plus 10 how much? 18 ohm. That's all, children. So first question over. Total resistance in the circuit is 18 ohm. Now total current. So to find the total current, I will apply by using Ohm's law. V by R I will take, since voltage V is 12 volt and this is 8 here. So you will get 4 by 6, right? Yeah. 3 4s 12, 3 6 18. 4 by 6 means how much you will get? Okay, if I say 0.6, okay, 0.667 or else 0.67 ampere we will get. Okay, so ampere units very important. Okay, 0.67 ampere children. So this is how you have to solve when series combination, when you are given the resistors in the circuit and when you are about to apply the combination of the resistors, first you should identify what combination they are in, series or parallel. Sometimes mixed combination also will be there. This is mixed, this is in parallel, this is in parallel, and the result this and this will be in series. So you should be very careful, and what you are supposed to calculate, again I am saying, while solving the numerical, given data and your requirement, very essential. So based on the requirement, if you want to calculate total resistance, yes, total resistance we have to calculate, or according to the given question, whatever they ask. In this one they asked total current, they asked, so total current means you need total resistance, but sometimes they may ask calculate the current flowing through this only, R1, R2, or calculate current flowing through R3 or R4, R5. So then also you have to apply this Ohm's law. Okay, so you can calculate such type of questions by using this combination of resistors as well as the Ohm's law. Okay, fine. So now let's move on to the next one. Elon Musk. Yeah, hello. Yeah, hi. Okay, see the next question. Heating effect of electric current. Okay, so resistance of the combination of the resistors we have done, we have completed. Next topic is heating effect of electric current. Very important one. When electric current flows through the conductor or the wires, then heat will be developed on its surface. Just like if you see this, if you are giving some X amount of electrical energy as input to the rotation of the fan, okay, so later if you touch after a few minutes you can find it as warm. That means only certain amount of electrical energy utilized to rotate it. Then what about the remaining? It's not loss in the form of electrical energy, but that will be existed in the form of some another form. That's what law of conservation of energy we have studied it as. So it may be now in this case it will be appeared as heat. So that development of heat due to the passage of current through the conductor, only we are calling it as heating effect of electric current. So heating effect of electric current is nothing but the phenomena of development of heat around the surface of the conductor due to the flow of electric current through it. So this heating effect of electric current was explained by Joules, and in honor to that we are having Joules Law of Heating, that named as Joules Law of Heating. Joules Law of Heating states that amount of heat developed, suppose if I say the conductor through the, this is the conductor through which amount of I current flows, and let the resistance of this conductor is R. For a time t the current is flowing, then according to Joules Law of Heating some amount of heat will be developed. That developed heat is directly proportional to flow of electric current through it. It is directly proportional to, square of flow of electric current flowing through it, directly proportional to resistance of the conductor, and the same heat is directly proportional to time of flow of electric current. So based on these three we can write H is equals to I square RT. H is equals to I square RT. This is Joules Law of Heating. Joules Law of Heating effect of electric current. It states that when electric current is flowing through the conductor, heat will be developed on the surface of the conductor. So that the phenomena of development of heat on the surface of the conductor due to the passage of electric current through it is called heating effect of electric current. It's explained by the Joule. Joules Law of Heating states that Joules Law of Heating effect of electric current states that amount of heat developed on the surface of the conductor is directly proportional to square of the current flowing through it, and directly proportional to resistance of the conductor, directly proportional to time of the current flowing, time of current flow through the conductor. So then H is equals to I square RT. In terms of voltage, suppose if you want to express in terms of voltage for a specific conductor, then we can write even in terms of voltage as H is equals to V square by R into T, like that. Okay, so this is how we can express. And this Joules law of heating, this heating effect of electric current, we are having plenty of advantages, such as we can make some toasters. See, these electric toasters, electric ovens or micro ovens. So in that, I mean, electric heaters also you may take, or electric iron box. In that, heating element will be used. Those heating elements generally made of alloy. Okay, generally made of alloy. Alloy is the combination of metals. Alloys will be having high resistivity than this general metals. Okay, so that's very important point. As they are having high resistance compared to metal, that's why alloys will be used in the manufacturing of electric toasters and electric iron box, etc. Okay, here one more important point. Alloys, basically alloys and metals, they will be having the resistivity as 10 power minus ohm meter to minus 8. 10 power minus 8 ohm meter to 10 power minus 6 ohm meter. This is for alloys. Alloys and metals. Okay, and for insulators, that will be some 10 power 12 ohm meter to 10 power 17 ohm meter. That will be the ranges. Insulators will be having very high resistivity. Okay, compared to alloys and metal, alloys and metals will be having low resistivity compared to insulators. But in that also, alloys will be having a high resistivity compared to metals. Comparison matter with what you are comparing. So here in this heating effect practical applications, so you may take as I said, electric toaster or iron box, or else a heater you may take. In that, alloys will use. Why alloys rather than metals? Since alloys will be having higher resistance than the metals. Next, they do not oxidize easily. They do not burn easily when they are exposed to the air. Okay, when they are exposed to the oxygen. So here, alloys do not oxidize easily. That's why we are using these alloys in the manufacturing of toasters. Okay, fine. So this is about heating effect of electric current. Okay, in fact, the heat is also form of energy, where SI unit of energy is Joule, and then other electrical energy conversions we'll discuss. After teaching the power concept, I'll tell you. Right, there is a question on this. 100 joule of the heat is produced each second in a 4 ohm resistance. Find the potential difference across the resistor. So here it's a single straightforward question. There is a resistor having resistance of 4 ohm and 100 joule of heat is produced per second. Time is in 1 second. 100 joule amount of heat is developed. What is the potential difference? Just now we know that H is equals to V square by R into T. This formula you can recall. H value here in this question is 100 joule. Potential difference is you have to find, alright. And if I bring time to this side, this is okay, fine. Sorry. See, bring time to this side, this is H by T, that is H by T is equals to V square by R. H by T value is 100 joule per second. So 100 is equals to V square by R value 4. So V square is equals to 400. Then V is equals to root 400, which is 20 volt. That's all. Or else the same question you can find by finding I also. First I will find I. How can you find I here? We know that H is equals to I square R into T. Another formula, Joules law of heating. Directly I recalled it. Then H by T is equals to I square R. H by T value 100 by R value 4 is equals to I square. So I square is equals to, that is 25. Then I is equals to root 25, which is equals to 5 ampere. I we know, then V is equals to IR. 5 into 4, 5 4s are 20 volt. Again you get the same thing. Okay, so you may use either that or this method, doesn't matter. So this is how you can find the heat developed in the resistance. Alright. Next one, electric power. Electric power in class 9 mechanics you have learnt work energy chapter. Power is nothing but the rate of doing work is called power. So similarly here when it comes to electric power, the rate at which electrical energy is consumed or dissipated. The rate at which electrical energy is consumed or dissipated is called electric power. It is called electric power. So this we will express in terms of power P is equals to, so I am recalling the same work done by time formula. So work is nothing but here electrical energy that is dissipated out. So this I can write in terms of voltage, potential difference as well as current. So we know that V is equals to W by Q, right? So then W is equals to VQ we can write. In the place of W, VQ I have written VQ by T. V is equals to Q by T, right? Q by T we can write it as V into I. Why? Since I is equals to what? Q by T, right? Okay, so power P is equals to V multiplied by I. This is one formula. So if you are applying Ohm's law, V is equals to IR we know. Then if you substitute here, P is equals to, we can write it as VI we can write, I square R we can write, V square by R also we can write. So these are further conversions. Okay. So SI unit of power. SI unit is watt. W-A-T-T watt. We can write like this. We can define 1 watt as if 1 volt potential difference is applied, then if 1 ampere current flows in a electric conductor, when a 1 volt potential difference is applied, then the power consumed or power dissipated by the conductor can be said to be 1 volt. That means 1 volt is equals to, 1 watt. 1 watt is equals to 1 volt multiplied by 1 ampere. So 1 watt is equals to 1 volt ampere. Basically this watt is very small unit. So we will express it in terms of kilowatts like that. Okay. So kilowatt is equals to 1000 watt. When it comes to general this motor mechanical device and all, we will measure that power in commercial units like horsepower. 1 horsepower is equals to 746 watt. This you have learnt in class 9. Okay. So this is about general things about electric power. The rate at which electrical energy is consumed or dissipated is called electric power. Power P is equals to, the expression in terms of current and voltage is V into I, and further conversions by using Ohm's law, you can write P is equals to VI or I square R or V square by R. So we will recall each whatever the required one while you are solving the numericals. Okay. Here you don't need to stick on to one particular formula. Based on the requirement, you have to recall the suitable formula. Alright. So this 1 watt is equals to 1 watt power will be dissipated or consumed when 1 ampere current flows through the conductor for a potential difference applied across it is 1 volt. Okay. Very important. Alright. So this electrical energy, this electrical power we can write in terms of energy also. So see here, power is equals to work done by time, right? So this work done nothing but energy consumed, energy consumed or energy dissipated, electrical energy. So electrical energy by time also you can write power is equals to electrical energy by time. So electrical energy, further you can write how energy is equals to power multiplied by time. Okay, based on that energy calculate, that one we are having numericals also. So let us see a few models on it. Yeah, there is a question here. You can see the question. An electric bulb is connected to a 220 volt generator. All right. The current is 0.5 ampere. What is the power of the bulb? What is the power of the bulb? Alright. So voltage is given, current is given. We know that power is equals to voltage multiplied by current. Okay. So then P is equals to voltage 220, current 0.5 here. Then 22 multiplied by 5. It will be 110 watt. 220 here one decimal, so 22 multiplied by 5. 25s are 100, 2 5s are 10, 110 watt. Okay. So like this you can solve. Next one, an electric refrigerator rated 400 watt operates 8 hours per day. What is the cost of energy to operate it for 30 days at 3 rupees per kilowatt hour? Very important, electricity bill calculation. See, it's very simple. First, you have to calculate the total energy consumed by the device. Whether one device is given or 10 devices given, same procedure. One device is given, we'll calculate for that only. If 2-3 devices are given, we will calculate for each and everything in the same format, and we will add the overall energy, we will calculate. So here, one thing here you should remember, children, this is kilowatt hour, right? 1 kilowatt hour is equals to 3.6 into 10 power 6 joule. This is in terms of joule. In electrical energy consumption, generally commercial units we will use. Okay, that is commercial unit of electrical energy is kilowatt hour. Very important. kWh, kilowatt hour. So in electrical terminology, 1 kilowatt hour consumption or dissipation is nothing but 1 unit of electrical energy. So while calculating this electricity bill, you may see even your electricity bill also. This month 100 unit consumption was there. Last month 220 units consumption. So they use it to express it in terms of units, right? So that each unit represent 1 kilowatt hour. Suppose if I have a consumption of, my domestic appliance consumption is, usage of electrical energy is 30 units. It means 30 kilowatt hour consumption. 50 units, 50 kilowatt hour. 60 units, 60 kilowatt hour. So 1 kilowatt hour consumption is nothing but 1 unit. So very important. Since here while calculating this bill, see here, they said 3 rupees per kilowatt hour. In some numericals, they may say 3 rupees per unit. So in such case, what is that unit meaning? Unit nothing but kilowatt hour only. 1 unit of consumption or dissipation of electrical energy is nothing but 1 kilowatt hour. So for this refrigerator, power is given 400 watt. It's operated for 8 hours per day. Total time I am calculating 8 hours per day, but for how many days you have to calculate? For 30 days. So total time 8 into 30, it is 240 hour. Then energy I am writing here, total energy per month, this is for month. Power multiplied by time, since energy formula just now I said, power into time you can express. Power of the device is 400, time is 240. So then this will become, so it is 96,000. This is watt hour. But to calculate that electrical energy, we have to express in terms of kilowatt hour. So energy consumed is equals to 96,000 watt hour, right? This you can convert into kilowatt hour by dividing with 1000. So then it will become 96 units. 96 kilowatt hour, nothing but 96 units. But here you are not having any problem since they themselves said kilowatt hour. So electricity bill per month is equals to 1 unit cost 3 rupee, 96 unit cost 96 into 3. So this is 288 rupees. That's all. Very important model. This is how you have to solve. Suppose if 2 more devices or 3 more devices are given, you will calculate the same method and you will add fully overall. You will add, each energy consumed will add, will find, and then we will add total energy will get, and then again same. If you are getting in kilowatt hour directly, that fine, that will be fine. If not, you have to convert further into kilowatt hour, and then you have to calculate the electricity bill. Okay. And apart from this, we are having in the heating effect 2 points I forgot to say about filament as well as the fuse. So fuse is the safety device which will use to protect the electrical appliances from the high due currents, like abnormal currents when flows, when overloading or short circuiting occurs, electrical current will flow abnormally, so due to which all these electrical appliances will be damaged. Okay, so in such case we have to use electric fuse to prevent them. Electric fuse will work on the property of the heating effect of current. So there a small fuse we are having nowadays MCBs, generally which is the fuse which is made of an alloy like lead and tin combination will use by keeping it in a closed porcelain casing, will fix it in the circuit in the main supply. Okay, phase wire to the in series with the phase wire will keep it. So when excess current will flows through that circuit, then automatically that fuse will be melted off. Fuse will be melted so that all other electrical appliances will be prevented. So here important point, how they lost the question. What are the characteristics of the fuse? Basically the fuse will be designed with a appropriate melting point. Generally it will be having low melting point, and as it is an alloy, generally as I said, a lead and tin combination, so it will be having high resistivity compared to other metals. Sometimes you can find the low resistance and all that. Actually high resistance or low resistance you have to write over there by keeping that comparison. So for this fuse you can say it's made of an alloy, it will be having low resistance low melting point, high resistivity, as I have taken here an alloy. Now we are having advanced fuses, what we are calling it as MCB, circuit breakers, to prevent from this short circuiting and all. Okay, another one, and this fuse ratings will be like 1 ampere, 2 ampere, 3 ampere, 5 ampere, 10 ampere. In that manner it will be designed. Tungsten is used as filament. Okay, tungsten is having high melting point. Its melting point is more than 3000 degrees Celsius, nearly 3380 degrees Celsius. So as its melting point is high and tungsten will be having high resistivity, so when the current flows through it, it glows. Heat energy will be, by the help of this heating effect of electric current, heat will be developed and it will be producing the light. Okay, so tungsten is used in the, it is used in the bulb as filament because it will be having high melting point, it will be having high resistivity, and it's not it will be filled generally with some like nitrogen, argon gases, which are inert gases. Okay, they won't exhibit any kind of further reactions. Okay, fine. So tungsten is made of a material which is having high, tungsten consists of high melting point and high resistivity. That's why we'll use it in as a to make the filament. Fuse, electric fuse will be having low melting point and high resistivity. Very important, children. Okay. Okay, then that's all about the today's session. So we have completed this electricity chapter in one shot today, and the next another session, one more lesson we are having, that is what magnetic effects of electric current, that will be held on coming 16th February. So we'll meet in the next session. Okay, hope you have understood and we are clear to you. If you are having any doubts still, you can download our Practically app. Just subscribe to the YouTube channel, Practically YouTube channel. There are plenty of videos you can watch subject related, and which are in the app you can find so much interesting data. That's with the help of 3D simulations and 3D videos are there. Okay, fine then. I am signing off for today. Thank you everyone.